we move on to a reversible isobaric process. Isobaric, and you know what isobaric is. Isobaric is basically no change in pressure. Now, when you have no change in pressure, what happens now? Okay, so we know that del Q by temperature is your ds, right? And we have studied before that at constant pressure isobaric processes, we have an equation something like this, okay? So del Q is basically the del H. So the amount of heat exchanged at an during an isobaric process is the enthalpy change. That's how it was defined, right? So in here, this whole thing becomes del H dH by T ds. So dH becomes T delta S. Okay, so now when you have dH is equal to TdS, you just got this T to the other side, and then you differentiate both sides with respect to temperature at a constant P, because this is a isobaric process. This becomes ds by del T P. Now this del H by del T P is basically Cp, right? So you have Cp, you bring this T to this side, this becomes del S by del T P. Now you bring the T to this side and integrate. So you bring this T on this side, and then you will have Cp by T times dt, and on this side you will have ds. So I'm just reversing the order and writing it here, that you have ds that you'll be integrating, and in this on this side you'll have Cp times 1 by T times dt. Now you'll be integrating both of these, and what you'll get is you'll get delta S becomes an integral of Cp by T times dt. Okay, this is very similar to what we saw earlier in terms of the isochoric process, right? So I'll just highlight this as equation in my book. It in here, Cp by T. This equation is 60, and this equation is 61 dH ds. This was 59. Okay, so this equation is very similar to this equation, right? So if you see this, the del S at a constant pressure is Cp by T dt, and at constant volume it is Cv by T dt. Yeah, you can get in an n here to show that there are n number of moles, but this equation and the one on the top at the constant volume, the isochoric process, are very similar, in which you just have the Cp for the constant pressure heat capacity and the Cv for the constant volume heat capacity. The Cp can be calculated as a function of temperature, and when you get that, you plot it, you put it in here, calculate the polynomial with respect to Cp, with respect to the temperature, and then you can integrate that. Okay, so doing that, you will get the amount of delta S for an isochoric process. Isobaric process. Okay, now the next we'll be doing is, so also this equation can be used for all types of materials, not just the gases. Similar for that. Now Cp, Cv, we have not taken any kind of assumptions in here. Therefore, the Cp and the Cv can be for any material. Okay, so you can calculate the delta S for any material. All right. So now what we do is we try and see the entropy change during a phase transition. Okay, so say there is a phase transition going on, and when you have a phase transition, there is an entropy change associated with that. So phase transitions happen at constant pressure and constant temperature conditions, right? So the phase, during a phase transition, the delta S is very simple. It is just the enthalpy of heat of that transition by the temperature. So using this, you can calculate the amount of entropy that is being exchanged. So this being equation 62, pretty simple in that way. Now, when you have entropy, till now we were trying to see the change in the amount of entropy. Now, the third law of thermodynamics takes us to the absolute value of the entropy. So we saw the first law, energy conservation, the second law, entropy. The third law of thermodynamics is it tells you that entropy is an absolute quantity, and you can actually calculate that amount. So what the third law tells you is what's the value of the absolute entropy. Now, this absolute entropy is for solids, liquids, and gases, right? It can be for solids, liquids, or gases. Any kind of material can have, like, can be any kind of phase, any kind of matter will have an entropy, and using the third law, we'll be trying to find out the absolute entropy of those kinds of matter. What the third law tells you is that at absolute temperature, so at 0 Kelvin, the entropy of any substance is 0. Okay, so this is the whole idea about the absolute entropy. So the entropy of a standard material, right, at 0 Kelvin is equal to 0, right? These are the units of mole, units of entropy. Okay, so at 0 Kelvin, the entropy of anything is basically, of any matter, solid, liquid, or gas, is 0, right? So this is basically the idea of absolute entropy. Now, if you want to calculate the amount of entropy at any other temperature than 0 Kelvin, what you'll have to do is just, so say we want to calculate the standard entropy for any substance at 298 Kelvin, right? So what do? You just integrate the entropy from 0 Kelvin to 298 Kelvin using the formula we just derived. So using this, you'll be able to find out the entropy. Now, this was delta S, okay? This was not S, so this was the change in entropy. Using this, which is the third law of thermodynamics, says that entropy is an absolute quantity. And therefore, if this is an absolute quantity, you should be able to find it. So we know that the entropy of any material at 0 Kelvin is 0, which is not known for the enthalpies, right? So we do not know the absolute value of an enthalpy. But in here, we know that the absolute value of an entropy at 0 Kelvin is this. For enthalpy, if you remember, we assumed, we chose a baseline from which we were trying to measure the enthalpy of a system. So we had to choose a baseline. So in here, the entropy is the absolute entropy, because at 0 Kelvin, we found that to be 0 units of entropy. So at any higher temperatures, how you'll do it, you just integrate it from 0 Kelvin to this. This becomes easy, because at 0 Kelvin, your entropy is 0. So this whole process becomes easier because the amount that you'll find in here will be 0. Okay, so this is basically the third law of thermodynamics. Okay, so we understood the first law of thermodynamics, which was energy conservation. We understood the second law of thermodynamics, which was calculating the amount of entropy exchange, and this is the third law of thermodynamics, which is telling that entropy is an absolute quantity, and the value of entropy of any substance at 0 Kelvin is basically 0. Okay.